Section 2 in our chapter about how matter can change is all about the behavior of gases. Now remember in section 1 we said that the first way that matter can change is in its state. It can go from being a solid to being a liquid to being a gas to being a solid again, all depending on how much energy those particles have. And solids, liquids, and gases have unique characteristics. Sometimes they have a shape that is locked in and solid, like a solid. Sometimes they have a shape that can change, like a liquid or a gas. Sometimes, if they have enough energy, they can even expand and have an indefinite volume. Focusing in on gases, the ones that can both change in shape and change in volume, we can learn a few interesting things. Gases, even though they're able to behave in sort of erratic, crazy ways, they're predictable in some other senses too. And so we'll talk about how gases are predictably going to behave and some of the expanded abilities that they have because of the amount of energy in their particles. The two objectives for this section are to describe 3 factors that affect how gases behave and to predict how changes in pressure or temperature are going to affect the volume of a gas. So gases are different from solids and liquids. They have the ability to change shape, and they have the ability to expand and fill any amount of volume that they're given. That could be the amount of volume inside a balloon, that could be the amount of volume in an entire room, or even in the atmosphere, depending again on how much space they're given. Gas particles, typically, if they're allowed to run free, will have a lot of space in between them. This is because gas particles have enough energy that they can bounce off of each other and go wherever there is room for them to go. The amount of space that gas particles take up is their volume. So if you look at that picture with the red moving balls all over the screen, the confines of that yellow rectangle are the amount of space, the amount of volume that gas is allowed to take up. Notice that those particles are filling all of the volume, all of the space that they're given. There are a few times when a gas gets to have so much temperature or pressure that they can even push on the confines of those containers and maybe expand them even more. Volume can change when it's affected by temperature and when it's affected by pressure. Temperature is a measure of how hot something is. The inverse of hot is cold. So sometimes people say the measure of how hot or cold something is. We're just going to refer to heat because heat is what does the interesting stuff. A more specific way to talk about temperature would be that it's a measure of the movement of particles. I want you to think back to when we were in the classroom still together. I made you do this really annoying activity where you had to get out of your chairs and I turned you into solids, liquids, and gases. Now, if you're remembering this activity along with me, you'll remember that some of you really didn't enjoy it because it meant that you had to get around or get up and you had to walk and you had to move and you had to move faster and slower depending on what you were, if you were a solid, liquid, or a gas. The reason I had to do that activity is because temperature, the amount of energy, the movement of particles, affects what kind of a state they belong in. It affects what they're able to do, how much they're able to expand. The faster the particles are moving, the more energy that they have. So if a substance has a really high temperature, that means that its particles are moving really, really fast. It also means that they're putting more pressure on the walls of their container. If you think about a bunch of people running around like crazy in a room, they might be banging off of the walls. They might be putting pressure on the confines of the space that they're in. Picture a bunch of kids in a bouncy castle. They're all moving around, they're all jumping, and they're pushing on the walls. If enough of them push in one direction, that whole thing might start to tip, right? They're exerting a lot of pressure. An object that has a low temperature has slower moving particles. Picture that same bouncy house, but now instead of jumping, the kids are just walking. There's less pressure on the sides of that bouncy castle, right? Less pressure, low temperature. Volume is a measure of the size or region that an object can take up in 3D space. So we're not talking about a 2D drawing on a piece of paper anymore, right? We're talking about something that has length and width and height. We're talking about something that takes up space in the real world. Volume is a measure of the amount of that space is taken up. The volume of a gas is going to completely depend on the container that that gas is in. If gas has the ability to expand to fill a whole room, you better believe it's going to want to do that. It's going to have to be trapped in order to keep it in a smaller space. And gas particles have the ability, even though they don't particularly enjoy it, to be compressed, to be squeezed together, to be held in a very high pressure. So what is pressure? It's the amount of force that's exerted per unit area on the surface. So imagine that you are in a classroom and the teacher walks in the door and the teacher says, guess what, guys? You have a test and it starts right now. That's a lot of pressure, right? Why is that pressure for you? Well, it's because the amount of time that you have to prepare for that test is super small, right? You have maybe 30 seconds before that test is on your desk and you have to start putting down answers. Imagine that you're in your classroom and your teacher walks in and says, all right, guys, you're going to have a test. It's going to be in 2 months. Are you stressed? Are you feeling the pressure yet? Probably not. Why is that? Because you have 2 whole months to prepare. So pressure in the real world, like you and I experience it, is very similar to the pressure that we talk about in science. Pressure is the amount of force exerted per unit area of a surface. When you have a lot of time before something challenging is going to happen, you can think of that as having a huge amount of surface area, right? You're not going to be as stressed, you're not going to feel as much pressure because you have all this extra time. If you have just a few seconds, if you don't have a lot of time, you're going to start to feel a lot of that pressure. Why? Because you have a whole bunch of stress, a whole bunch of pressure exerted in not a lot of space, not a lot of time. Pressure is the number of times, and we're talking about a gas at least, that a particle is going to hit off of the side of a container. So if you think about the jar that we saw in the last slide that had the stopper, where sometimes it was pulled out and the gas had more space to run around in, and sometimes it was pushed so that the container was smaller and the gas had less space. The gas particles haven't gone away, right? They're the same number, but now they're hitting off of the sides of the container in the smaller version of the container more often. We call that fact that they're hitting more often an increased force, an increased pressure. There's the picture again, just so you can visualize it perhaps a little bit better. Volume 1 versus volume 2. There's more pressure in volume 2. Now for the gas behavior laws. Remember that a law is never going to change. A law is a prediction of what's going to happen 100% of the time. There are actually 2 laws that are associated with the way that a gas behaves in terms of temperature, pressure, and volume. Boyle's law states that the volume of a gas is inversely proportional. In other words, is opposite the pressure of a gas when the temperature is constant. This law was discovered in the 17th century by an Irish chemist named Robert Boyle, hence the name Boyle's law. Now, Charles' law was developed a little bit later, and it's a law that states that the volume of a gas is directly proportional, in other words, the same as the temperature of a gas, as long as pressure stays the same. So in both of these examples, we have a constant, that's the variable that's not going to change, and then we have either inversely proportional, meaning that they're going to be opposite one another, or directly proportional, meaning that they're going to be the same as one another. Let's take a look at these in a little bit more depth. So here we have a picture that illustrates Boyle's law. Notice all the gas particles inside of the container. In the very first iteration of the container, which is the one on the far left, we have the piston pulled all the way out so that those gas particles have a pretty decent amount of space to take up. And in the example on the far right, we have the piston pushed down so that those gas particles take up or have a far smaller space that they are able to take up. So when we lift the piston up all the way, the gas particles can spread apart. The pressure is going to decrease. They have more space to exist in. They are going to have less pressure exerted in the walls of the container. Now, if we look at the picture again on the far right, when we contract that piston and we decrease the amount of space that those gas particles have to exist in, now the pressure goes way up. So all Boyle's law is saying is that if there's a lot of space, there's not a lot of pressure. If there's a tiny amount of space, now we have a ton of pressure. So the amount of space is inversely proportionate, it's opposite the amount of pressure. If we have a lot of space, the opposite would mean we don't have a lot of pressure. And if we have just a little bit of space, then the opposite would be we have a lot of pressure. They're inversely proportional. If you have a lot of space, it's going to be the opposite with pressure. And if you have a little space, it's going to be, again, the opposite with the amount of pressure. There's a video on my website that I'd like you to watch that illustrates Boyle's Law. It's kind of entertaining. If you have a syringe like this at home, you could always try it at home as well. Now, Charles' Law has to deal with temperature and how temperature is going to impact volume. Remember that Charles' Law was dealing with something that was directly proportional. So we should see these numbers, these calculations coming out to be about the same. So again, we have two pistons. One of them is pushed way down so that those particles don't have a lot of space. They don't have a lot of volume. And then in the other image, the one on the far right, the particles have a little bit more space because the piston is drawn up. If you look again at the picture on the left, you'll notice that because the temperature is reduced, because those particles are moving more slowly, they have less energy, they need less space in order to exert the same amount of pressure. If the temperature is increased and if those particles are given more energy, they're going to be moving faster. Now they need more volume in order to have the same pressure, in order to exert the same amount of force on the edges of their container. So temperature is going to be directly proportional, the same as pressure. When temperature goes up, pressure goes up. When temperature goes down, pressure goes down. Oops, here's a video that I'm going to put on my website as well that illustrates this principle of Charles' Law. Please give it a watch after you finish the lesson video, just to help you understand what's happening here with temperature and pressure a little bit better. The homework for today is a homework assignment. You'll notice it is on my website. If you have questions about any of this, the gas laws make common sense, but they can be hard to understand the first time that you hear them. So if you have questions, feel free to stop by our Hangout this afternoon or shoot me an email if that Hangout time doesn't work for you or if you miss it because you haven't watched the video yet when that happens. Totally understand. But let me know how I can help. Have a great day.